So if we have the ability to take the derivative of an inverse function, then maybe we can figure out how to take the derivative of e to the x, because we already know how to take the derivative of its inverse, right? If we know that y equals e to the x, then we know that x equals negative natural log of y, right? We take the natural log of both sides of the equation, and we can rewrite the equation in terms of x is in terms of y. So that is something we actually know how to take the derivative of. Remember, the goal, find dy dx. We've got y written in terms of x here. Here we've got x written in terms of y. We're still looking for dy dx, so we're going to take the derivative with respect to x on both sides of the equation. And that's something we've done already, right? We've done implicit differentiation. So when we take the derivative of the natural log of y, we get 1 over y times dy dx. And then when we take the derivative of x with respect to x, that's about as easy as you can hope for, we get 1. So if we solve for dy dx in this new equation, we get dy dx equals y. The derivative of y is itself y. That's fascinating. We've never seen that before. Whenever we take the derivative of something, it changes, but the derivative doesn't change when we take the derivative here. That's a fairly interesting property, and I don't think you're going to find too many functions that fit that property. Y equals e to the x is fairly unique as far as that's concerned. What we're really seeing here is that the derivative of e to the x is itself e to the x, right? Because that's what y is in the equation above. Or more generally, if we don't have x in the exponent, but we have something more complicated, that's the composition of functions. So we still get the same e to the u back again, but we also have to remember the chain rule. So multiply by u prime. So that's a nice derivative pattern, right? All we have to do is whatever we have raised to the e, we still have, whatever we have e raised to, we still have e raised to. We just have to remember the chain rule. Or if you prefer, we can write it as 2e to the 2x. Okay? Over here, when we remember the chain rule, the derivative of x plus 2 is simply 1. So this is something where we get the exact same thing back again. Over here, well, this is not going to get the exact same thing back again, but it gets partly that. But then the next piece would be, don't forget that chain rule. The derivative of x squared is 2x. So we can write it either way. I kind of like it better this way, keeping the exponential term at the end. And then lastly, there's really no trick here. You're just going to take e raised to the sine of x. That's this part right here, and then don't forget the chain rule. Derivative of sine of x would be cosine of x. And that's it. So now that my dog has successfully scared away the UPS delivery folks, we've got this interesting looking equation here. We've got an equation that there's no hope at all of solving for y, right? We've got y's inside exponents. We've got y's inside natural logs. I can't solve this for y. So if I'm going to talk about slopes, then I'm definitely going to want implicit differentiation. So that'll be the first step, is find dy dx. I'm going to take the derivative of 1 and get 0. I'm also going to, well, before I take the derivative, let's go ahead and expand this out using properties of logs. And the reason I would do that is so I could avoid the product rule. So I guess I should leave the 1 there, even though it's going to go away. The derivative with respect to x of the left side of the equation is going to equal the derivative with respect to x of the right side of the equation. So when we take the derivative of 1, it's gone. Derivative of natural log of x is 1 over x. Derivative of natural log of y is 1 over y dy dx. And then on the right side of the equation, e raised to a power differentiates to e raised to that same power. And then don't forget the chain rule. Now, people will forget the parentheses here, but that's bad. Make sure that when we take the derivative of this argument, this x minus y, we're multiplying the whole thing, right? So that's going to be 1 minus dy dx. At this point, you could solve for dy dx. That's perfectly fine. But I kind of like the idea of, if I know what x and y are, I like the idea of just putting them in there, in this current form. It reduces the need for a whole bunch of extra algebra most of the time. So 1 over 1 is 1 plus dy dx, which is 1 dy dx, right? Equals e raised to the 1 minus 1 is 0 times 1 minus dy dx. Well, e to the 0 is 1. So we have 1 plus dy dx equals 1 times 1 minus dy dx. Okay, add dy dx, subtract 1, divide by 2, we get dy dx equals 0. So this is a place where we have a horizontal tangent line. This might be kind of a fun thing to graph. I'm not really sure what it looks like, but at what the point 1, 1, we would expect to have a horizontal tangent line. What about at -1, -1? Let's take a look and see. Again, take that blue equation and put your x values of -1 and -1 in for x and y. We get -1 minus dy dx equals, well, it's still e to the 0 times 1 minus dy dx. Oops. So e raised to the 0 is still equal to 1. So we get 1 minus dy dx here. And interestingly, when we try to solve for dy dx here, when we add dy dx to the other side, we're going to get no more dy dx. We're going to get 0 or -1 equals 1, which is definitely not true. So looks like we're going to get an undefined value. Undefined. So it might be nice to see what's going on the graph. Maybe we can kind of make heads or tails of what's going on here. So let's pull up a graph. And you might find that some calculators are unable to graph this implicit equation, 1 plus the natural log of x times y equals e to the x minus y, but I think Desmos will do an okay job of it. We've got 1 plus the natural log of x times y equals e raised to the x minus y. We've got these puzzling little dots right here. Perhaps it has to do with the fact that the natural log function has a restricted domain. But I'm interested at figuring out the slope at 1, 1. Okay, well that looks like a horizontal tangent line to me. I'm also interested at the slope at -1, -1. Well, the function appears to be differentiable, nice and smooth and curvy, no sharp turns, but take a look at that point, -1, -1. Why would we get undefined there? I think you guys are seeing it. Got a vertical tangent line, right? So the slope of a vertical tangent line is undefined, so that's why we're getting an undefined value at -1, -1, while we're getting 0 at 1, 1. Fantastic. All right, so what else do we have here? Okay, here's a little shout out to stats teachers around the world. This is the equation that creates the bell curve of a normally distributed population, I think is how it goes. And the area under this curve is 1, which is another nice thing to think about, right? But not what we're talking about right now. We're asking for points of inflection. It should be pretty clear that this bell curve has a concave up, changing to a concave down, changing back to a concave up sort of graph, right? We're expecting 2 inflection points. How do we find those inflection points? Well, we take the second derivative and figure out where it changes signs. So y prime equals 1 over root 2 pi. Where do they get that root 2 pi? It's nuts, man. But that's just a scalar constant, so that doesn't do anything. And then we'll take the derivative of the other part, which is going to be e raised to that same thing back again. But then don't forget the chain rule, multiply by the derivative of that exponent, so that's going to be -x, right? The 2's cancel out, and we're going to get -x. Or, to put it a little nicer, I'll put the negative out front. I'll keep that constant separate because that's not really going to do much in this problem, I don't think. And then we'll have times x times that same exponential expression that we started with. Okay, that's our first derivative, so we can use that to determine when the function is increasing and decreasing, although I think we have a pretty good sense that it's increasing from negatives infinity to 0 and decreasing from 0 to infinity. So let's go ahead and move on to y double prime, the second derivative. So that scalar constant of negative 1 over root 2 pi is still just hanging out there, but now we've got a product of variable expressions, so we have to use the product rule. We've got the derivative of x times e to the negative x squared over 2 plus x times the derivative of e to the negative x over 2. Well, we just did that. It's going to be the same thing back again, right? Negative x over 2, and then multiply by another negative x. All right, well, this looks a little scary, but let's see what we can do to simplify this a bit. We can definitely factor out that e to the negative x over 2, x squared over 2, because that seems to never go away, right? It's just always there. And when we factor that out, we have just a 1 left in the first term, and x times negative x is left in the second term. So this is our second derivative, and we're interested in when this thing changes signs. Well, set that equal to 0 then. What happens if I try to set e to the negative x squared over 2 equal to 0? E raised to the what equals 0? In other words, the natural log of 0 equals what? It's nothing. There's nothing at all. There's no solution. You're never going to get 0 when you raise e to a power. So we only care about 1 minus x squared equal to 0, which gives us the answers of x equals plus or minus 1. So that's an interesting little factoid for you. At x equals negative 1, which is 1 standard deviation to the left of the mean, and at x equals positive 1, which is 1 standard deviation to the right of the mean, that's exactly where our concavity changes. We're concave up, concave up, concave up until we hit negative 1, and then we're concave down until we get to positive 1, and then we're back to concave up again. And just to double check, find the points of inflection. So I guess we'd have the point 1, comma, well, plugging in a 1 into here, we get e to the negative 1/2. So that's 1 over the square root of 2 pi e. Who would have thunk it? And then over here we've got negative 1, comma, 1 over the square root of 2 pi e. Those are our 2 points of inflection.